All right, welcome back. So our next speaker is Joseph Tassarotti. Joseph was a professor at Boston College, an assistant professor up until about a week ago, and starting next week he will be an assistant professor at New York University. I think the main focus of his research is formal verification, but he's made multiple contributions to probabilistic programming. He's worked on the compilation of probabilistic programming languages and on inference at scale. And he's now working on formal verification aspects of probabilistic programming. The talk that he will present today is formally verified compilation of probabilistic programs. Well, welcome, Joe.
Thank you. It's always nice to be introduced by someone who the work is joint with. So yes, so this is joint work with Jean-Baptiste, and also Sam Steitz, who's a PhD student at Northeastern, who was advised by Jan Wilm. I should also acknowledge and thank Xavier, both for inviting me to give a talk here, but also for some help he's been giving us with understanding how to integrate with CompCert, which is quite essential to the project, as we'll see. So since this is an audience with a mixed background, and I want to make sure we're all on the same page, I'm going to spend a little time to lead up to things. So if you're familiar with various parts of what I'm saying, please forgive me as I get everyone on the same page. So the starting point for this work is the same as the motivation for a lot of work in programming languages and formal methods, which is the observation that programs are buggy. Okay, and this is not a shock. In fact, we heard a rousing description of the kind of bugs that plague software. So a look at the news on any given day is enough to tell us that these bugs can sometimes have horrific consequences. And of course, as computer scientists, we're aware of this problem, and we seek to address it. And there are a variety of approaches. People do things like write extensive tests or write bug-finding software. And while that's great, it's by no means sufficient to eliminate the occurrence of bugs. So an alternative, complementary approach is to formally verify the correctness of software. So one style of formal verification makes use of a tool called a proof assistant. Okay, so you can think of this as a piece of software that can check sort of arbitrary mathematical proofs. And the idea is that a software developer, after writing their program, can also write down a specification, or spec, which is a mathematical description of a program's intended behavior. And then they can construct a proof showing that the program adheres to its specification. And the proof assistant checks that proof and tells us whether it's actually mathematically valid. All right, so the first time I heard about this, I thought it was kind of mind-bending. So let me just say a little bit more about what this looks like, since I think it's somewhat unfamiliar to some of this audience. So the idea here, right, is we can take some sort of arbitrary program, and then the proof assistant has a facility for making a theorem statement, a claim about the program's behavior. And then there are built-in what are called tactics that let us sort of apply the rules of logic to step through the program's possible behaviors and show that they're all covered by what we claimed in our theorem statement. So this methodology has been applied to a variety of software systems. Of particular relevance to the talk today is the fact that it's been used to build formally verified compilers. Right, so these are compilers that come with a proof showing that the output of the compiler, the assembly code, or whatever that you're going to run, has the same semantics as the original program that you inputted. Okay, so the seminal work here is CompCert, which is a formally verified C compiler, verified with the proof assistant Coq, developed by Xavier Leroy and colleagues. And then CakeML is another compiler that came a few years later for the ML, an example of an ML language, which was verified in the Hall proof assistant. So over the past few years, or no, over the past year, Jean-Baptiste and I have had this project unimaginatively called ProbCompCert, where the goal is to develop a verified compiler for the STAN probabilistic programming language. And as the name suggests, the idea here is that we're going to connect to CompCert. So ProbCompCert implements sort of a front end for STAN that emits C code, which is then compiled down to assembly by CompCert. So we get a sort of connected end-to-end proof about the overall system. And while it's somewhat intrinsically exciting, I guess, to have a verified stand compiler, there's also some aspects of compilation for probabilistic programming languages that are challenging and haven't necessarily been considered in that prior work on compiler verification. So in particular, of course, it's somewhat intrinsic to the very nature of probabilistic programming languages that we have to seriously contend with randomized behavior. Additionally, these languages have a somewhat complex runtime, not something that you would find in a standard language. Maybe we have garbage collector and something for CakeML, but the runtime that actually implements sampling and inference for these probabilistic programming languages is a new frontier. And then finally, of course, they rely upon a somewhat sophisticated mathematical foundation. So there's a lot of probability theory, measure theory that underlies these things, which again doesn't show up in, let's say, traditional compiler verification projects. Okay, so now that I've given a little bit of overview of the work, let me say a little bit more precisely what I mean when I say we want to verify the compiler. Okay, and what that means is I'll have to say more precisely what this specification, this mathematical description of the compiler's behavior is going to be. And to do that, I'll have to say something about the semantics, the meaning of stand programs. So as a starting point, let's look at how we would specify a conventional compiler and state its correctness. So at a high level, a compiler we can think of as a function that performs a translation between two languages. So we can think of it here, C is a compiler for some high-level language down to a low-level language. And the usual specification, what it means for the compiler to be correct, is that we want compiled programs to refine the original program. So if we take some program E here, and we run C on it, so we get C of E, the output, we want the behaviors of C of E to correspond to the behaviors of E. And we usually write this in this refinement notation, which is this square subset symbol. At a high level, you can think of that as saying that the behaviors of our compiled program should be a subset of the allowed behaviors of the original program E. So if we want to translate that to the setting of a probabilistic programming language, the very first question we need to answer is, what is the behavior of a stand program, right? And this actually is a little bit of a subtle question, okay, because there are several ways that one can run a stand program. There's kind of the classic MCMC sampling, but there's also built-in backends that support variational inference and maximum likelihood estimation. And I would say these all have sort of different guarantees or properties. So to narrow the scope here, in ProbComCert, we're just trying to build a verified implementation of the MCMC sampling runtime. And schematically, we can think of MCMC sampling as being built up into several components here. So we're organizing the compiler and its runtime in these three boxes here. So the sampler runtime is what's driving the Markov chain Monte Carlo algorithm. It's determining whether to accept or reject a sample. These samples are generated by another component, the proposal generator. So this comes up with candidates that the runtime must either choose to accept or reject. And as part of making that determination about whether to accept a sample, the runtime calls code to calculate the density of the model at a candidate proposal. And so in particular, this makes use of code that's starting with the original program and compiled down into something executable that can be used to calculate the density. And now the overall correctness property that we want from such an MCMC sampler is that in some sense asymptotically, as we generate more and more samples, the distribution of the generated samples should approximate or converge to the posterior dictated by the data and the model. Okay. So this is a complex property, this overall correctness. But what we can do is break this down and talk about the correctness of each of these schematic components in this diagram. All right, so in the first phase of the project, we're just looking at the density compiler component. So let me zoom in and say a little bit more about what's going on there. So stand programs are divided up into blocks. And I would say the core block is what's called the model block. So here's a simple example. Here we're sampling some parameter alpha from a normal distribution in beta, and then doing simple Bayesian regression and sampling output y. So what this model block does is it specifies how to compute the log of the posterior density of our model. So you can think of it as a function that takes in an assignment of data and a candidate for parameters and gives us back a real number representing the logarithm of the density. And the job of the density compiler is to take this model block description and emit executable code that actually calculates this function. And I think it's important to stress at this point that in Stan, the model block is really a specification of how to compute a density. It's not restricted to what I would call generative process modeling. So it's not an operational description of how to generate a piece of data by sampling. So in particular, when we write down this sampling notation, what's really going on is that that's sugar for manipulating an implicit variable that's called target, which kind of keeps a running tally of the calculated density. All right, so the sampling statement is really converted to adding some value to that target variable. In particular here, if we're sampling from normal, then what we do is we add the logarithm of the normal density at the value of alpha that we're currently considering for that parameter assignment. And then at the end of the model block, we can think of there being kind of an implicit return statement that returns back the value of target. All right, so this has important implications for how we actually do compilation, which is why I stress this. So to give a semantics to these model blocks, we use a hybrid approach, which involves two steps. So first, we give an operational semantics, which you can think of as a series of small step rules that tell us how to compute the expressions and statements that we see in the model block. And if you squint hard enough, that statement and expression language is kind of like a little mini C. Okay, so we can reuse some machinery from CompCert for describing the operational semantics of C programs. And then on top of that, we give a denotational semantics in which we interpret that density as defining a probability distribution on the parameter space. And so I should say that this is inspired by the approach that Caranova et al. Used in their slick Stan work from 2 years ago, or three years ago now, at Popple. So we're doing it slightly different here, but it's very heavily inspired by that decomposition they have. So I think the operational semantics, as I say, it's reminiscent of a little mini C language, so that's not necessarily super exciting for many people in this audience. But the denotational stuff is a little bit different than what you'd see in many languages semantics. So let me say a little bit more about how that works. So we have a model block that tells us how to compute a logarithm of a density. And really, to be more precise, it's only telling us how to compute that density up to some normalization constant. So now if we're given some assignment of data, this model density implies a distribution on parameters. So formally, we can obtain that by integrating over parameter space and normalizing. Okay, so we would say, given some measurable subset of parameters A, the probability of A is proportional to what you obtain when you integrate over that region, exponentiating the model block, right? Because it's a logarithm, so we need to exponentiate to get the actual density. Okay, so one subtlety here is that to be super precise, right, we are talking here about some measure theoretic integral here. And if we want to actually mechanize this and formalize everything in Coq, right, we would have to teach Coq, so to speak, all of the necessary measure theory for carrying out this proof in the proof assistant, right? So that would be a bit of a bummer since that's a lot of math to do, but there's an important shortcut that we can take. So in particular, Stan has a restriction that parameters ought to be continuous. And so we don't need the full generality of measure theoretic integration to describe the semantics for the purposes of compilation. So in particular, we can restrict to just talking about integration of rectangular subsets of parameter space. And so that lets us, instead of giving a full general measure theoretic integral, we can instead just use an improper Riemann integral over that space. And that'll be sufficient for talking about the semantics for our purpose. Okay, unfortunately, very conveniently, some people, Sylvie Bordeaux and Guillaume Melchion, have already formalized the improper Riemann integral in Coq, so we can just re-leverage what they've done. Okay, so using that, we can give a semantics to a stand program. And so now that we know what we want to really happen here in terms of what the meaning of the program is, we can say more precisely about what the compiler should do. So, given some stand program E, we'll say the denotation of E is precisely that function that maps a data assignment to a measure on parameters. And then the goal of the density compiler is that it should preserve this denotation. Okay, so the implied function from data to measure of the compiled program should be the same as the original. Okay, great. So now that we have said what it is we want to prove, let's talk about our strategy for actually doing the proof. And so here we're going to, besides directly building on top of CompCert, we're going to draw two important lessons, I would say, or ideas that are implicit in CompCert's verification. So first is that we're going to decompose compilation into many small intermediate passes. And second, we're going to make use of a proof technique called forward simulation. So the first of these, right, so CompCert, I guess we heard this morning that probabilistic programs are like elephants. So the saying, if you want to eat an elephant, you should do it one bite at a time. I guess if you want to compile an elephant, you should do it one pass at a time. Okay, so to break up compilation, what we can do is decompose it into many small passes between intermediate languages that have well-defined semantics and are simplifying the language. So this is the pipeline in CompCert, or at some point was the pipeline from CompCert from its reference manual. So each of these little red boxes is an intermediate representation of a program as we go through the process of compilation. And each of the arrows is doing some transformation that is sort of lowering a C program down to the ultimate target, which I guess in this pipeline is PowerPC assembly. All right, so the advantage of this, besides letting you do things one byte at a time, is that you get modularity in the proofs. So if we tweak one aspect of this pipeline, it doesn't break all the proofs of the other parts, and so this makes it kind of feasible for this to be developed incrementally, so we can go piece by piece. Okay, so we're going to use this same idea in the context of prob CompCert. So our pipeline is, well, the diagram is not as impressively drawn, and it's also not as deep, but we still have a bunch of passes here. Okay, so the details of all these passes aren't so important, but each of them is kind of, you can think of eliminating one of the features of a stand program and bringing us closer to a C-like program, where finally we end up at CompCert's C-Lite, and then at that point we can switch over to CompCert and finish compilation down to assembly. Okay, so we've broken it up into pieces, but we still have to figure out how to eat each of those bytes. All right, and so the proof technique we're going to use is simulation. So let me say a little bit more about that. So the canonical proof technique, in some sense, for doing semantics preservation proofs is a backward simulation. So we have two programs, E1, our original source, and our compiled program, E2. And we want to prove that E2 is equivalent or refines E1. Right, so a backward simulation proof, what we do is we exhibit, or we've come up with some relation R that relates our original starting programs. And then what we need to do is show that R is preserved as the program takes steps. So in a backward simulation, what we have to show is that for each possible thing that E2 could take a step to as we execute, we need to show that we can exhibit something that E1 can step to in 0 or more steps, call it E1 prime, which is also related to E2 prime by this same relation R. Okay, and we have to do this process repeatedly. So when we take another step of the compiled program, we have to show that we can simulate that in the source program. All right, and we prove that this is an invariant preserved for an arbitrary number of steps, and at some point, right, we get down to some return value of our compiled program, and then we'll show that that's related to the return value of the source program. Okay, and the idea here is when we get down to those final return values, if our relation R implies that they're equivalent, then we've kind of covered, showed that the possible behaviors of our compiled program are a subset of the allowed behaviors of the source program. However, the difficulty here is that it can be hard to come up with this relation R. In particular, we have to show that each step of the compiled program can be related back to some steps of the source program. All right? And as you can imagine, the compiled program maybe is doing more low-level steps. And so it can often be difficult to describe the intermediate states of the compiled program in terms of steps of the original source program. So an alternate technique is to use a forward simulation. And this is exploited heavily in CompCert. So in particular, if the program that we're working with is deterministic, then our simulation can go in the other direction. So rather than considering steps of the compiled program, we consider steps of the source. So given a step of the source program, we can now have to show that there's some number of steps of the compiled program that brings us back into kind of synchronization with the source program. All right, and it's similar, just from the opposite direction. But the advantage here is that it's often easier to explain a single source step in terms of some number of compiled steps, since they're less kind of low level. All right, so I think like a key insight, or at least the key lesson I took away from CompCert, is that if you make this observation about determinism, you can vastly simplify your life by going this direction for simulation proofs. Okay, so now at this point, when I explain that we want to make use of the same idea in prob CompCert, the question that immediately pops into the mind of the person I'm talking to is, how can you possibly use forward simulation if our MCMC sampler is a randomized program? You just told me that determinism was an essential part of the proof. Okay, but the answer here is that the overall runtime is randomized, but the calculation that takes place inside of the model block, the thing that we're compiling, is deterministic. All right, so even though the overall system is randomized, because the model block is deterministic, it's still valid to use forward simulation for thinking about compilation of the model block. Okay, so when we want to use forward simulation in our context, right, we are not just talking about preserving the operational behavior of the program, but also talking about preserving its denotation. That is, showing that these measures we get are the same. So in particular, we want to know that when we integrate, the measure we're going to assign through integration is going to be the same with our compiled program and with our original. Right, so we want to show that it's proportional to the original program's measure. Okay, but that we are indeed going to get that because the standard simulation that I just talked about will imply that our compiled model block for some given assignment of data and parameters will actually return the same exact value as our original model block code. Okay, so the density computation gives us the same value. So if your integrand is the same, then the integral is going to compute the same thing. Okay, so that's wonderful. Now, if we are, so as much as possible, we would like to use this forward simulation proof technique to show semantic preservation. Okay, and so if we look back at our pipeline, all of the passes here in yellow kind of follow straightforwardly that strategy because those passes don't really change the calculation that the model block is doing. However, there are some passes in which life is not so simple. All right, and two in particular I think are interesting are the sampling statement pass and reparameterization. So let me talk a little bit more about what's going on there. So I said that the sample statements in Stan are basically a kind of syntactic sugar for some manipulation of the target variable. All right, so when we sample from alpha, really we're just adding some density to our running target calculation. However, that was a slight simplification. Okay, in actuality, Stan is a little clever. Well, it's very clever, but here it exhibits some of that cleverness because it also drops addition of constants when we're doing this translation. So if you have a target increment, like here on the left, where we say that the target, we're adding on to it f, some function f of some variables, plus a constant d, then as part of this translation, it's licensed to, and in fact does, drop the addition of d. Okay, so this, the first time I saw this, I was a little alarmed, right? Because a standard compiler better not do that. I guess unless D is 0, it better not do that, right? You can't just change the calculations that I'm doing in my program. You can't manipulate what I'm adding. So why does this make any sense at all? Well, here is why it's so important that we have to take the denotational perspective, not just the operational one. Right? So this dropping of an additive constant is justified because if we go back to the fact that what we're going to do is ultimately integrate the exponentiated density, right, then really what's happening is that we're just scaling the integrand by some constant. Okay, and so that's going to be overall proportional once we normalize to the original version where we didn't have that constant. All right, so again, this is not, I mean, to the stand people, the audience, this is obvious, right? But to someone trying to formalize this proof, right, we need to spell out all these details to the proof assistant and explain why it's correct. So this is a little bit going beyond the simulation proof we saw earlier. Another pass that involves such a transformation that's a little non-conventional is reparameterization. So in Stan, we're allowed to specify that parameters have a constrained range. Okay, so when you declare some parameter of your model, you can say that it's lower bounded. So here alpha, we're going to say cannot have a value below 0, or we can give an upper bound, so saying here that beta can't have a value bigger than 1, or we can apply both lower and upper bounds. And there are other constraints, but for our purposes, we'll just talk about these three. Okay, so even though the model is written down saying that there's constraints on the parameters, when the MCMC sampler runs, it operates over unconstrained parameters. So how do we bridge this gap? Well, there's a phase in the compiler where we unconstrain or reparameterize to get rid of these. So the idea is, if you said, for example, that alpha has a lower bound of b, then when we actually compile this and run it, we're going to sample some unconstrained value, alpha prime, say. And then what the compiler does is it inserts a prologue in the model block to convert between these constrained and unconstrained representations. So at the very beginning of the model block, what we'll do is assign alpha to be some function of alpha prime. So we'll exponentiate it and add b. Okay, and if you think about it hard enough, you'll be able to convince yourself that this implies that alpha has a lower bound of b. Okay, so we insert that prologue, so that seems natural enough, fine, you're just mapping between two representations of a variable. But there's a third thing that has to happen, which is that we also insert as part of the prologue the addition of an extra constant, here it turns out to be a constant, the addition of an extra value to the target, which is the Jacobian of this transformation we're doing. Okay, so not only do we change the representation, we actually change the density that's going to be returned. Again, at first I was a little alarmed like this, like how can you just add on this extra value? Well, to convince ourselves that this is correct, okay, we have to recall first year calculus, right? What's going on here? Well, we're doing a change of variables in that integrand that I was writing before, right? So when you do a change of variables, you need to scale things by the derivative of the mapping that you're inserting here, right? So since we're working in log space rather than multiply, we add something, but that has the same effect. Okay, again, this is, I think very standard to the statisticians in the audience, but it's a little bit unusual for a compiler to do this kind of transformation. Okay, so how are we going to handle these? Well, even though this goes beyond the scope of what we saw before with simulations, we can still make use of the simulation proof technique, just slightly generalizing it. Okay, so the idea is we're going to factor the proof into two phases, kind of mimicking the two-phase construction of our semantics. So as a first step, we're going to use a simulation proof to show that the compiled model, rather than computing the exact same density as the original, is going to compute some kind of pure function of that original density. So you can think G here is perhaps scaling by a constant, or is inserting the Jacobian, or what have you. And then off to the side, we can separately do a denotational proof showing that the result of integrating that transformed value is going to give us the same, or up to a normalization by a constant, the same measure on distributions. Okay, so we use simulations for the operational half, and then kind of off to the side just do some math, some basic calculus to show that the measure we obtain is nevertheless the same. Okay, so now we get to the part that's fun for me. So this is ongoing work, okay? So I want to now explain to you one of the open questions or challenges we still have here, with the hopes that maybe in correspondence afterwards you'll tell me how to solve my open problem, or at least give me some consolation and agree that it's hard. So everything I've been sketching you to so far hinges on the idea that the denotation of the program is kind of working over exact real numbers, right? But in actuality, of course, what's really going on is that Stan and ProbCompsert make use of floating point arithmetic. Okay, so we're not, in fact, doing some integrand, right? Really, at best, this is some kind of discrete model in the real world where we're summing over the finite approximates of these real numbers, and rather than being able to say sort of arbitrarily large or small real numbers, we're constrained to what's representable by floating point numbers. All right, so in particular, beyond that, of course, when we do things like dropping addition of a constant, we're not perfectly scaling the logarithm, right, because there's some rounding error when we add things. Similarly, the Jacobian we obtain, right, the transformation we're applying is not a continuous remapping. It's got some approximations and some round off, since the mapping is going to use, a floating point exponentiation instead of an arbitrary real exponentiation. Okay, so what do we do? Well, as a first pass, we can just not address this consideration, right? So that's the strategy we're currently adopting. It's very expedient, right? So we're doing the denotational semantics currently in our proof, treating floating point calculations as if they were real arithmetic. In some sense, under the hood, I mean, this is what Stan is this is the mental model that's going on in Stan, right? Some of these transformations in some sense are not semantically preserving, but nevertheless, people are happy with them. So that would be one approach. Another idea would be to actually try to be very careful and not say that we are preserving exactly the semantics, but that we are approximating the semantics of the program when we do compilation. So we could try to bound the floating point error and actually say something more precise about what's, how off are things when we do these kind of transformations. Besides being very difficult, the aspect of, that I don't know how to handle with that approach is that ultimately, right, we're compiling some sort of arbitrary program given to us by the user. And the degree of floating point error that's introduced by these transformations seems to me like it must depend upon the program, right? So it's hard for us to do an analysis of how much error is introduced in kind of a generic black box way unless we were to try to statically analyze a program, perhaps. But that seems really tricky. Okay, and the last idea, perhaps, is to try to be more honest about things and do real exact arithmetic. Okay, I have no idea if this is even tractable, right? Of course, people have implemented various prototype languages and calculators that do exact real arithmetic. It's unclear to me whether you could do MCMC with such a model, but it would be kind of interesting to see if it would work. And then we could say, honest to goodness, that we're in some sense doing an integral over arbitrary real numbers. So I'd be really happy to chat with people and see what they find most satisfying here, or maybe they don't find any of this satisfying and think the whole idea is in trouble. But I think it's an interesting problem. There's been some work on MCMC algorithms and accounting for floating point error, but again, to the best of my knowledge, those were looking at precise models, some fixed model rather than some arbitrary procedure. Okay, let me wrap up just to conclude, right? So the overarching goal of this project is to build a verified compiler for Stan. Today I talked to you about the first phase that we're in the middle of, which is to build this verified density compiler. And the two sort of ideas, which are really just re-leveraging ideas from Compsert, is that we structure things in intermediate passes, And we try to re-leverage forward simulations as much as possible, but we do so by, on top, making use of an auxiliary denotational argument. Okay, thank you so much, and happy to take questions.